In this unit, we'll look at how the memory requirements for streams compare to other data types that could be used to represent the same data. We'll then move on to see why it's important to estimate the memory required for a stream and begin to think about how we can control that. For many use cases with large datasets, streams can require significantly less space than other Redis data structures. As we saw in the previous module, streams are implemented using a radix tree data structure, an extremely efficient way of storing key value data. The Redis streams implementation contains a further optimization to reduce memory usage, field name compression. When multiple consecutive messages have the same field names and are appended to the stream, Redis will not replicate the storage of the field names. Instead, each subsequent message having the same set of field names is marked using a flag, rather than repeating the same field names over and over. This means that you can save memory by having the same structure for a series of messages in a stream, while retaining the flexibility to change that structure over time. Let's compare the memory used by a stream with that required for a sorted set. We'll experiment by storing the same data using both data types. The Python example code adds a configurable number of entries to both a sorted set and a stream. In the case of the stream, IDs begin at 1-0 and are incremented by 1 for each entry. For the sorted set, scores begin at 1 for the first entry and are incremented for each subsequent one. In both cases, the data stored is a simple string hello plus a sequence number. Once the entries are created, we use Redis's memory usage command to compare the number of bytes required to store each of the two representations of the data. Let's run the code to generate a stream and sorted set, each containing 1 million entries. The output tells us that in this case, the stream is substantially more memory efficient. The sorted set takes up just over 3.5 times the memory used by the stream implementation. In this example, the size of our data is very small. We're just storing the string hello and a number. As the size of the data stored increases, the relative difference in memory usage between the sorted set and the stream implementation will decrease. This is because the data itself becomes a larger percentage of the size of both data structures. If you are choosing between whether to use a stream or sorted set, you may wish to try a small experiment like this and see what the space savings could be with your own dataset. A stream processing approach is commonly chosen when working with a dataset that has the potential to grow indefinitely. For example, a stream of temperature readings from a fleet of IoT sensors has no logical end to it. Redis does not, of course, have the ability to retain an infinitely growing dataset. A Redis server will reject write operations when it runs out of memory. This means that it is important to manage the size of a stream so that it doesn't grow on forever. Remember that consumers read from the stream, but do not cause messages to be deleted from it once consumed. You need to manage the stream's length separately. When using streams, it's important to understand how much memory you might need for your specific dataset and the options available to you to manage that. In this unit, we saw how streams can be more memory efficient than other data structures. Next, we'll look at some common strategies used to control the length of a stream and how each can be applied to Redis streams specifically.